vectors. The lines L and M have vector equations. Given that L and M intersect, show that 2b minus a equals 4. So we can start off by using the column vectors. This is minus 1, 3, 4, minus 1, 3, 4. And this is 2 minus 1 minus 1, 2 minus 1 minus 1. And here we have 5, 4, 3, 5, 4, 3 plus mu times AB1, AB1. So use column vectors so we can see better. Now, since they intersect, the corresponding components should be equal. So for the x component, minus 1 plus 2 lambda must be equal to 5 plus a times mu. And for the y component, 3 minus lambda must be equal to 4 plus b times mu. So here we can just solve for lambda or mu. Here if we multiply the second equation by 2, we get 6 minus 2 lambda, 8 plus 2b mu. And for the first equation, just rewrite exactly the same, and we can add here. So we add to cancel out the lambda, eliminate lambda. Now minus 1 plus 6 is 5, and 5 plus 8 is 13, and a plus 2b is a plus 2b times mu. So we can subtract 13 from both sides and divide both sides by the brackets. We get mu in terms of a and b. So now we do the same thing but with two different another combination of two equations. So we are still using the same y component from the y component, but now we are using the z component for the next equation here. Okay, so we use the z component, and again we find mu equals something in terms of a and b. In this case we can simply subtract because minus 1 minus minus 1 is 0, so they cancel out actually. Now 3 minus 4 is minus 1, 4 minus 3, b minus 1 is b minus 1 times mu. So we can subtract 1 from both sides and divide by the brackets. We get mu in terms of b only actually. Okay, now since we have mu equals something from the second equation and the first equation, we can just combine them. So minus 2 over b minus 1 equals minus 8 over a plus b. So we equate the two equations, and then there are many ways to do this. We can start by dividing both sides by minus 2. So minus 2 divided by minus 2 is 1, minus 8 divided by minus 2 is 4. So now we cross multiply 1 times a plus b, we get a plus b, and we have b minus 1 times 4, and then just 4 times b, 4 times minus 1, and we want to move everything with b to the right here. So 4b minus 2b is 2b, and we move the minus 4 to the left, so it becomes plus 4, and the a to the right becomes minus a, and we get what we need to prove. The next part, given also that L and M are perpendicular, find a and b. So previously we know the L and the M vector equations. Perpendicular means the dot product equals 0. So perpendicular dot product equals 0, but we have to use the direction vectors, not the position vectors. So these are random points on the line, and these are the directions. So we use the directions. Dot product equals 0. So dot product means we multiply the corresponding components. So 2 times a minus 1 times b minus 1 times 1. So if we rearrange a little, we get minus b plus 2a equals 1. And remember from the first equation, from the previous part of the question, we have this, just rewrite, and here we can just add to cancel out. We have 3b equals 9, so the b equals 3. To find the a, we can just use one of the equations here. I'm just using this equation, replace the b with 3, and we get the value of a. When a and b have these values, find the position vector of the intersection. So previously, we know this is one of the line equations. We are using this line equation because in the previous working, we already know mu equals this in terms of b. And from the previous question again, we have the values of a and b. So we can just plug in the value of b here. We get the value of mu. Now we have everything we need. We have the mu, replace it with -1. We have the a and the b, replace with 2 and 3. So therefore, the intersection point would be 5 minus 2, which is 3. 4 minus 3, which is 1. 3 minus 1, which is 2. So we have the intersection point. That's it. I'll see you.